There was, in the beginning, an endlessly small concentration of matter. This mass experienced a massive outburst that started the creation of molecules, atoms, stars, and galaxies observable in the present day. For many years, this has been the science-based interpretation. Nonetheless, new investigations have introduced a different point of view, arguing that the universe may not have originated as early as once assumed. Instead, it might be part of a regular process in which the universe goes through repeated phases of growth and contraction, a cycle that may never end. Brian Cox, a distinguished theoretical physicist, has also expressed doubts regarding the Big Bang hypothesis, which asserts that something cannot arise from absolute inertia. This type of uncertainty introduces an enticing element to the ongoing debate. In addition, findings from the James Webb Space Telescope have shown data that challenges the idea that the final event marking the commencement of the universe was the Big Bang. This prompts a profound inquiry. If the Big Bang wasn't the origin of the cosmos, then what was? Join us as we begin this expedition into the origins of the universe, where we will delve into the limits of the Big Bang theory and examine this mystery along with numerous others. If you want to stay up to date about discoveries regarding the universe and its larger context, you should subscribe to our platform, press the like icon, share this video with more people, and enable notifications. Researchers have constructed a comprehensive understanding of the cosmos during its earliest phases, commonly known as the Big Bang theory. As outlined by this paradigm, the universe in the past was much smaller, significantly hotter, and incredibly denser than it is now around 13.8 billion years ago. During that period, the elements that make up our environment were produced within mere minutes. Our entire universe, including its stars and galactic structures, was originally compressed to the size of a small fruit resembling a peach with an extremely high temperature exceeding 1 billion degrees. Amazingly, this remarkable account aligns reliably with all present-day empirical results. Space scientists have examined everything, from the lingering electromagnetic radiation left over from the beginning of the universe to the distribution of the lightest chemical elements, concluding that all observations are consistent with the forecasts made by the Big Bang framework. Based on the state of our current understanding, this portrayal corresponds closely to the actual nature of the universe. Still, despite its apparent strength, the Big Bang theory is acknowledged as lacking some elements. A crucial component is missing from this explanation: a complete comprehension of the universe's very first moments. This issue stems largely from the constraints imposed by our physical models. The blend of Einstein's theory of relativity and advanced particle physics provides us with a useful conceptual basis. Nevertheless, as we probe further into the earliest epochs of the cosmos, the mathematical difficulty escalates dramatically, eventually reaching a stage at which existing techniques do not produce useful answers. One piece of evidence for this problem is the postulated existence of a singularity, a condition of infinite density at the start of the Big Bang. This concept literally means that the universe was once compressed into an immeasurably tiny and dense condition, which appears illogical. To confront this problem, it is necessary to investigate previously unexplored physics, develop strategies that go beyond current limitations, and provide a more complete perspective into the universe's first moments. Our current methods and theories in science are not advanced enough to resolve this issue. Thus, we must establish new principles of nature capable of explaining the core forces of nature, including gravity, under extremely intense energy circumstances. This is exactly where string theory comes into play. The goal of this hypothesis is to provide a scientific structure that combines gravity with the other essential interactions, especially in areas of extremely high energy. In essence, string theory proposes that it can provide an explanation for the initial stages of the universe's existence. Within string theory arises the idea of an ekpyrotic universe, derived from the Greek term for conflagration or blaze. This suggestion states that what we perceive as the Big Bang was triggered by an earlier occurrence. That is, it was not the ultimate beginning but part of a continuing sequence. Extending this concept has contributed to the formulation of the corresponding theory known as cyclic cosmology. Although the idea of a repeating universe has been pondered for thousands of years, string theory now delivers a rigorous mathematical foundation for this vision. Under the structure of cyclic cosmology, the cosmos operates as though it exists forever, alternating between huge outbursts and subsequent collapses in a perpetual rhythm that extends into both the present and the future. This example of a cycling universe was introduced by the esteemed scientist Roger Penrose, a Nobel Prize winner. Penrose was intrigued by a striking resemblance in mathematics between the origins of the universe defined by extreme compactness, heat, and density shortly after the Big Bang end. The faraway future universe is characterized as extremely cold, expanded, and almost void of substance. His theory asserts that, within the most extreme limits, these two circumstances result in something mathematically non-distinct. The sum, despite appearing contradictory, suggests that matter's emptiness might actually be the mechanism that generates all existing material in the cosmos. From this vantage point, the Big Bang appears as what largely remains undetectable. Matter has, in fact, been absorbed into black holes and then eventually vanishes into dispersed photons within an immense vacuum. What is the source of the universe? This could be interpreted in a different way as close to absolute inertia. Yet this inexistence continues to be a kind of something that constitutes a physical universe, albeit one devoid of content. The method by which the same condition can be perceived as both a frigid, empty universe and a hot, condensed universe depends on perspective. The crucial insight lies in a sophisticated mathematical method known as conformal transformation, which changes the size of an item while maintaining its form intact. Penrose made the point that the cold, vacant state and the hot, dense condition can be connected by using this kind of mathematical scaling. When aligned in terms of the structure of spacetime, despite their scale differences, they may be regarded as fundamentally equivalent. Penrose, on the other hand, contends that in such extreme physical circumstances, the concept of scale loses its significance. In cyclic cosmology, a young, hot state replaces the old, cold one. The existence of the hot and dense phase is simply a continuation of the state that was cold and empty. However, this cause and effect relationship violates the common understanding of time, as both time and size lose their traditional meaning when taken to such extremes. These two states belong to separate timelines, suggesting that, from the perspective of an observer within his own cold, personal temporal framework, the desolate state appears to continue endlessly. In this domain of cyclic cosmology, science, philosophy, and ideas are closely related. Cosmological simulations provide theoretical and extensive accounts of the beginning of these cycles. But even if Penrose's views gain traction through the development of the universe, a more profound philosophical dilemma endures regarding the ultimate origin of tangible reality. How did it all begin? When do regular phases start? This provokes the classic question, why is there any existence at all, rather than nothing? This remains one of the most fundamental subjects of metaphysics. For our exploration, we will adhere to the restrictions of physics, considering three possible explanations for the beginning of these cycles. 1. It is possible that there is no scientific explanation at all. 2. Another idea is that there is no end to a series of cycles in which each cosmic iteration represents a distinct universe with fundamental quantum conditions shaped in some way by the preceding one. 3. Finally, there is the hypothesis of a single cycle of repetition where each brand new universe is explained by characteristics inherited from the conclusion of the previous one. These choices are appealing because they do away with the need for mysterious events and provide a more complex interpretation that works within the framework of science. Inside the sphere of physics, Penrose describes the concept of an endless series of universes shaped by his knowledge of quantum mechanics. In quantum mechanics, a physical system can exist in multiple potential states before being observed, at which point it abruptly transforms into a particular state. Penrose proposes that each cycle is altered by unpredictable fluctuations in the quantum world, creating unique differences between cycles. These theoretical possibilities are intriguing for experimental researchers, as they imply we might find faint traces or irregularities in the radiation that remains from the beginning. What do you think? Share your thoughts in the comments section. If you enjoyed this presentation, don't forget to press the like button, subscribe to our channel, and share this video so that it reaches an even wider audience.